So, hey everybody, thank you so much for coming to this talk. The edge has become a very popular application of the distributed systems, but what exactly is the edge? The edge is simply something that runs very close to clients geographically. So when we think of services such as DNS resolution, content delivery, and IP firewalling, which are close to the client, these are things that we consider near the edge. And traditionally, we have considered things like relational databases, which have lived closer in centralized data centers, which are further away from clients. So we can see that the edge is really just a relative metric, where services that run closer to the clients are considered more edgy. Location-based network latency and costs are massively reduced when we can serve requests from clients at the edge of the network, closer to where they are. So, hi everybody, my name is Justin, and I'm a software engineering intern at Apple, building out services for iCloud's Edge network. Previously, I worked at Cloudflare as a systems software engineer, focusing on storage infrastructure, multi-tenant resource isolation, and even database internals, where Vignesh was my super amazing engineering manager. And then Vignesh has been an engineering manager at Cloudflare from 2019 up until now. He's been running the entire software storage infrastructure org, as well as the database team. And he's also worked on the startup that he's working on called SpinUp.host. He also is a member of PGUS. And from 2016 to 2019, Vignesh gained a lot of database engineering experience at the ground level as a database engineer at Ticketmaster. So today, I'm excited to share with you guys how we design and operate our entire high availability database architecture at the edge. Together, we'll break down in high detail the high availability setup and consider the trade-offs that we had to make around each part of the system. Then we'll explore some of the interesting performance challenges that we faced when bringing our database infrastructure closer than ever to the edge and dive deep into the solutions that we've implemented. We'll finally take a sneak peek at some of the really interesting recurring patterns that we see emerging in relational data storage co-located at the edge. So today, just some quick numbers. Cloudflare is the market leader in network security, performance, and edge computing. So for some cool numbers, let's give you guys an idea of what the scale we're dealing with. We have over 27 million internet properties that depend on our protection, which means that our network needs to handle over 46 million HTTP requests per second on average at any given time. We leverage our network point of presence locations spread across 250 locations globally. So this level of traffic translates into over 55 million row operations per second on average against our busiest Postgres database cluster. And that stores over 50 terabytes of data across all of our clusters. Now, Cloudflare's control plane is an orchestration of many microservices that power our API, our dashboard. Our control plane manages the rules and configurations for critical network services along the data path. So our database clusters store things like DNS record changes, firewall and DDoS mitigation rules, API gateway routes, and even data for internal services like billing entitlements and user auth. So we've commonly seen application teams frequently use Postgres in some pretty interesting ways. Since Cloudflare began, stored procedures have been commonly used to execute business logic as units of work. The robust P-SQL language enables intricate branching logic, which we've used for enabling and disabling domain zones with transactional consistency.
Will be turned on. That's what.
We've also commonly seen applications where service teams will use Postgres as an outbox queue for capturing domain events.
Once he's done.
One example is when DDoS rules are generated from traffic analysis in a centralized data center. They're first written into a Postgres table.
So he's first, and then
a separate daemon will typically pull these events from Postgres and pipe them through Kafka to services at the edge. This means that latency-critical services can avoid directly hitting the database while enjoying the durability that Postgres and Kafka gives. So keep in mind that at Cloudflare, we're running our entire software and service stack on our own bare metal hardware. So unlike many other major service providers, we spend a great deal of time considering things like rack-mounted servers, network cards that power our high-bandwidth backbone, and the operational maintenance required. On-premise data storage offers us the highest degree of flexibility across the entire stack, We can meticulously fine-tune elements such as our solid-state RAID configuration. And we've even implemented features in the open source cluster management system and even have applied custom performance patches against PostgreSQL itself. This level of transparency and control over our system would otherwise be impossible had we used any managed vendors such as AWS RDS. But unfortunately, that also means that there's no magical auto-scaling button that I can just push and immediately increase capacity when we start experiencing load. And so I would say this is one of the most challenging aspects of running Cloudflare's entire stack on-premise. So let's dive into Cloudflare's database architecture that sits near the edge. We need to process transactions on the order of millions per second. When designing and selecting the components of our system, we tried to consider what was most needed from an ideal architecture. And so the most important thing is high availability. The control plane for our critical services need to remain available 24/7 to protect our customers. Initially, we aim for an SLO of 5 nines of availability across all of our services. And that means that we get 5.5 minutes of downtime per year across the entire software stack. This gives our databases even less leeway. Achieving a high level of availability requires our system to operate at an immense scale. And so our transactional workloads typically skew on the read-heavy side. So our infrastructure has to handle a high rate of read RPS and write RPS with minimal latency, as well as maintaining fault tolerance. Of course, we also care about observability, which is important in any distributed system, but for the purpose of this talk, we're leaving it out of scope. So we internally leverage our Anycast network, which means that clients are naturally load balanced across our PG Bouncer proxy instances. This is the first step of our journey in pushing the databases to the edge, since queries can be processed faster in closer proximity to the clients. While BGP Anycast allows us to proxy queries to the optimal region closest to the clients where they're deployed, write queries still need to be forwarded all the way back to the primary region where the primary database instance resides, while read queries can be locally served from the closest nearby region. So here's a picture of our entire massive architecture, but let's just start from the very top at the proxy layer. So at the top, we have PG Bouncer. This manages database server connection pools used by our application clients. Queries are then passed through HA proxy, which are load balanced across several database cluster instances to prevent any single Postgres database from becoming overloaded with a disproportionate number of queries. So in the middle, a typical Postgres deployment contains a single primary instance, which replicates data to multiple replicas. And this is done to support a high rate of read queries. Our primary database handles all of the writes, and our asynchronous and synchronous replicas handle reads. Our Postgres cluster topologies are managed by the high availability cluster management tool called Stolon. It's backed by the etcd distributed key value store, which underlying it uses Raft protocol for leadership consensus and election in the case of primary failovers. You'll notice that we have adopted an active standby model to ensure that we have cross-region data redundancy. Our primary region in Portland serves all inbound queries, and at the same time, our standby region in Luxembourg is ready to handle all incoming traffic if we ever need to evacuate the region or fail out. This means that our primary Postgres cluster replicates data across regions to our standby as well. So there's a lot going on in this high-level diagram. We'll dive into each layer and dissect each of the components and the trade-offs that we considered. So I'm going to hand it off to Vignesh.
All right. Thanks, Justin, for the nice introduction. I appreciate that. So we decided, hey, we have to build this highly distributed and relational database using Edge. So when we wanted to set on to do this, we wanted to look at what are the fundamental things that's going to basically define the way how we define the architecture. So as the first principles, we looked at CAP theorem. Since it's a distributed application, which we know is going to be distributed geographically, and especially using open source software, Postgres, and also everything is built on our own data centers. So just a quick recap on CAP theorem. For any distributed applications, you can have only one of the two. Either you can have consistency or high availability. And a lot of the times we pick availability over consistency. Let's go over the cases where we pick the trade-offs and what are those trade-offs. So this is a typical architecture of how we deployed in a single data center. There is a primary database, and then there is a synchronous replica, and then if you look at it, at least we have a couple of asynchronous replica. The same kind of topology is replicated across multiple data centers. We have at least right now 3 core data centers where we have replicated at real time. So why do we pick this kind of a semi-synchronous replication topology where we have the primary database and at least one synchronous replica and a bunch of asynchronous replica? So in a typical situation where we have like an asynchronous replica which goes down, we don't have any problem with respect to the applications. The applications can still continue working without any impact because it's just an asynchronous replica. Similar trade-offs we made for cross-region replication. Let's say we have a replication, a region in Europe as well as in Asia. If either of those two goes down, still our applications in the US can continue working well. However, if the synchronous replica goes down, we basically bring the entire application to halt because we didn't want it to take any kind of reads and writes, so especially writes, without making any trade-offs. Pretty much every time when there is a failover that happens on the primary database, we pick the synchronous replica to be the new primary. And that's the reason why we have this kind of a semi-synchronous replication topology that we went with. So, as I mentioned earlier, there are two fundamental things. One, it's going to be based on top of Postgres, and two, everything based on on-prem. Postgres by itself is not distributed database. It's started in 90s in Berkeley, and it's been designed with monolithic architecture at mind. So how are we going to take this Postgres into a distributed Postgres? Two things. One, we rely heavily on the replication aspects. One is the logical replication, and the other one is streaming replication. There is a third derivative, what I call the cascading replication, which is basically built on top of the above two ones, either logical or streaming. So before we get into the replication and how it's useful for us to build the distributed Postgres, I wanted to have a quick primer on write-ahead logs. How many of you are aware of write-ahead logs? That's pretty good for some of them. Just a quick overview. So, I mean, in general, in any database, not just in Postgres, whether you pick MySQL or Oracle, all this fundamentally relational database management systems achieves the durability in ACID using write-ahead logs. In a simple terms, whenever you make any change to your database, it doesn't need to be synced directly on your file system or the database files. Rather, you can capture those changes sequentially in a basically a log file. And then those log files are synced to your database files, in an asynchronous fashion. So this provides the durability options that we pretty much need in any database systems. And that's pretty much turned out to be a really good feature for us to build a replication mission or replication systems, where we capture these changes and then replicate out to another replica. Right, so going into the streaming replication mode. So in streaming replication mode, it's pretty simple. A replica basically creates a TCP connection and streams pretty much every log entry from operations within a transaction to another replica. And the interesting part with this streaming replication is that it's pretty performant in the sense that we can pretty much capture any changes that happens at pretty much like 1 terabyte per second changes, even to the replicas on the other end. Minimal delay, so pretty much, there are delays. We have seen, Justin will go over some of the delays and how you can create those delays, but in general, that it's pretty performant. The other caveat with streaming replication is it's all or nothing. So if you set up a replica, then you have to pretty much replicate every single data because it's based on the file system level, block level. There is no way for us to, at least so far, optimize which data is being replicated. The more newer version of replication is logical replication. As the name suggests, it's more at the logical level instead of the block level or the foundation level where you are replicating data by blocks. Rather, in logical replication, you are replicating data at the SQL level, where each SQL statements that are captured at the end of the transaction, and they are like replicated on the other hand. More like if you can think about like a publisher and subscriber option. Definitely more flexible compared to the streaming replication. Here you can create publishers and subscribers even at a table level, and even more granular at a row level and on a column level. So you have like a much more flexibility than, let's say, a streaming replication provides. However, it has two caveats that really, that's a hindrance for us, at least as of now, to adopt logical replication. The biggest one is the schema changes. No DDL changes are replicated. So you have to kind of figure out some way, build like custom tools where when you have to make some changes, replicate those changes to all the other replicas. That's just not easy. The other bigger problem is that logical replication is still not performant at scale. For a cluster, probably, maybe gigabytes of size, maybe it's good, but not at least at the terabyte, multiple terabyte scale. Logical replication is not yet there. Right. Cluster management. So yeah, pretty much, one of the biggest reasons we would have a cluster management, as we all know, database failures, right? Whether we like it or not, failures do happen for multitude of reasons, right? Like as simple as that, hey, we have a logical failure, like a data corruption happened on one of the primary databases, and what do we do? Or even more like severe things like natural disasters and whatnot. So in any of those situations, we have to trigger a failover, and doing them manually is not fun. And another fact, at least 5% of hardware at any given time is kind of faulty, pretty much. If you think about it, on a fleet of like multiple thousands of servers across multiple data centers, at pretty much any point in time, you have like some kind of failures that is always going on. It could be as simple as like a RAID failure on a disk, all the way up to like a availability zone going down. So how are you going to be prepared for these failures without having a good cluster management? So we picked Stolon, which is a pretty thin layer running on top of the Postgres clusters itself. It's open source software written in Go, started in probably, I guess, 2018 or 19. It started picking up. The features that really brought us to use Stolon is, one, it's Postgres native, right? It speaks Postgres. And also it supports like multiple site redundancy, like in the sense that you can deploy a single Stolon cluster which is distributed across multiple like Postgres clusters. Those clusters can be located in single region, or even they can be distributed across multiple regions. There are a few more interesting aspects. One, it provides like a failover. Obviously, that's what you would expect from your cluster management tool. But the good thing is it's more stable. In the sense, we have seen very less like false positives. So digging deep onto our cluster management, the first component is keeper. Keepers are basically the parent process which manages the Postgres itself. Any changes that has to happen has to go through this keeper. So you can think about like keepers as basically the Postgres process. Then there is the sentinels, which are basically I would consider them as the orchestrator, which looks at the health checks of each components of Postgres and then makes decisions such as like, hey, is the primary healthy, or should we should we start an election and figure out who the new primary should be. And finally, the proxy layer, where all the clients connect to it, and then proxy layers make sure that where is the right primary is. We should avoid any kind of, let's say, like multi-master situation, etc. So over to Justin, where he's going to dig down into the connection pooling and the HA aspect.
Nice. So finally, database connections are a finite resource, which means that we need to manage them efficiently. Now, we all know that there's overhead when you go and open a new TCP connection or Postgres connection, but what's actually happening under the hood? Well, first, Postgres connections are built on top of the TCP protocol, so it requires that three-way handshake. Following this, we also have an SSL handshake to secure that communication. Also, Since Postgres dedicates a separate operating system level process for each connection, the main postmaster process has to fork itself to execute queries for the connection. This forking, as we all know, involves a new page allocations and copying memory from the parent process to the new child address space. So in other words, each connection requires a non-zero amount of time of CPU time, and this consumes finite resources such as memory. Now, when we have thousands of these connections open concurrently, these three steps start eating up a lot of CPU time that should otherwise be used for transaction processing in the execution engine. So a server-side connection pooler will open a finite number of connections against the database server itself, while exposing a black box interface that matches the same wire protocol that Postgres supports. So clients can connect to the pooler the same way they would connect to the database for queries to be sent. Managing pools in a separate server allows us to recycle previously open connections while minimizing the total number of open connections in the database server. But it also allows us to centrally control tenant resources for each client, such as the number of allocated connections. And so internally, we've actually done a lot of work in forking PG Bouncer and adding a lot of interesting features that take inspiration from Vegas congestion control algorithms to actually give us stricter multi-tenant resource isolation. But that's also a little bit out of the scope for this talk. So in our specific setup, we opted for PG Bouncer as our connection pooler. Like we said, PG Bouncer has the same wire protocol as Postgres. Clients just connect to it and submit their queries like they normally would. We particularly chose PG Bouncer because to shield clients from the complexity of database switches and failovers. So instead of clients having to think about, hey, where's the new database when it failed over? Where should I connect to? Instead, PG Bouncer manages this and abstracts it away. PG Bouncer operates as a very lightweight single process server, which handles network I/O asynchronously. So this allows it to handle a much higher number of concurrent client connections as opposed to Postgres. PG Bouncer introduces an abstract concept known as client-side connections. Now, this isn't the exact same as this is not the same as a direct server Postgres connection. When a client establishes a new connection, it obtains one of these client-side connections from PG Bouncer. PG Bouncer then multiplexes these queries in an end-to-end fashion, where queries originating from various client-side connections are relayed across actual Postgres server-side connections, and they go through HA proxy. So why is PG Bouncer so lightweight? Well, PG Bouncer employs a non-blocking model to handle network I/O efficiently. So unlike the traditional approach of allocating a separate thread or process for each TCP connection, such that that Postgres follows for compute-bound requests, PG Bouncer utilizes a single thread that just executes a single event loop, meaning that we only need one thread stack space for all the required connections. There's, however, a bit more complexity in managing the state for all of these clients. The loop monitors sockets for read and write events using the epoll mechanism. So instead of polling actively and spawning a new thread on each new connection in user space, we just need to tell the kernel, hey, these are the file socket descriptors that I want monitored, and let the kernel do the rest. We then call epoll wait in PG Bouncer, which then just tells the operating system, put me to sleep. I don't need to do anything until you let me know that put me to sleep and until you let me know that TCP packets have arrived to this file descriptor and tell me and notify me. And then the kernel just simply raises a hardware interrupt and provides PG Bouncer with the associated file descriptor. So we can process logic in user space, such as making an authentication call to Postgres, PG Shadow, before forwarding off the query, making it a memory-efficient solution for managing and relaying between a large number of client-to-server connections. One of the interesting challenges we've had with setting up PG Bouncer is having multiple single-threaded PG Bouncer processes utilize all the CPU cores on a single machine, because it is a single process program. However, we wanted them to all listen on the same port. So how could we reduce complexity for application teams where they don't have to think about, oh, which port should I go to for a specific PG Bouncer process? Luckily, we looked to the operating system again for a solution and found that you can bind multiple TCP sockets from different processes to the same port. So we've actually patched PG Bouncer in open source to use the SO reuse port socket option when opening a new TCP socket to listen on. And finally, let's just chat about load balancing. So we use load balancers, which front our Postgres instances to distribute incoming database queries across multiple Postgres servers. Specifically, we've chosen HA proxy as our load balancer. Using round-robin load balancing has been an effective way to distribute queries evenly across Postgres instances, while preventing any single instance from becoming overwhelmed. Similar to PG Bouncer, a load balancer such as HA Proxy also provides high availability and fault tolerance by automatically routing traffic away from failed or unresponsive Postgres servers to healthy ones, which avoids any downtime from degraded database instances. We use HA Proxy to relay TCP connections at layer 4, incurring minimal overhead. And fun fact, it uses the kernel splice system call, which just attaches an inbound and outbound TCP stream in the kernel. And this means that data received from the inbound TCP socket is immediately transferred to that outbound socket and forwarded without having to be copied into user space. So now we get to the fun part. We're going to dive into some of the interesting problems and challenges across our database infrastructure and share some of the cool performance tips and tricks that helped us in our journey to high availability at the edge. By the way, I think that's an actual image of Vignesh when we see one of these problems. So first up, replication lag. We found that our Postgres replication lag becomes extremely pronounced under heavy traffic, especially for applications who have many auxiliary or redundant data structures and schemas, such as bloated indices. In these cases, write operations become amplified because we're updating them in the primary, rebalancing our index B plus trees on disk, and we also need to replicate that as well. Other bulk-heavy write operations such as ETL jobs, data migrations, and even mass deletions for GDPR compliance are also common offenders. So another interesting cause of replication lag is automatic storage compaction, otherwise known as auto-vacuum in Postgres. This just executes on interval, so when the data is deleted, fixed width tuple slots become fragmented on disk, so we have this process that goes ahead and cleans up those fixed width data slots, and so that avoids any sort of fragmentation. Now, replication lag is an unavoidable problem in any replicated distributed system, since data needs to cross the network path. Internally, we target an SLO of 60 seconds of replication lag, and we tell this to the upstream application teams, which we work with. So to minimize the replication lag, we, number one, try to batch our SQL query writes into smaller chunks to avoid replicating large blocks of data all at once. One way we also sidestep replication lag and maintain read after write consistency is by caching or reading directly after writing to the primary or the synchronous replica. Finally, we can avoid replication lag by simply ejecting all replicas from the cluster, leaving only the primary. No replicas means no replication lag, right? Now, while this might sound insane, this approach requires a deep understanding of tenants' query workloads and potential changes in volatility. And so that might significantly change the system's resilience. So you can think of this as kind of the unsafe keyword in Rust. So another interesting incident, one of our largest public-facing incidents happened back in 2020, where a series of cascading failures severely impacted our database's performance and availability. Our public API services experienced a drastic drop in availability, plummeting all the way down to 75%, while our dashboards for other critical network services were becoming 80 times slower. So from what we saw, both regions' primary databases had executed a failover and promoted their synchronous replicas cleanly. However, the primary database in the primary region soon started to crumble under the massive load of RPS traffic. And so as a result, this led to a second failure of the new elected primary database, and that left us with no more synchronous replicas to promote. Now, this is starting to sound like the beginning of a high availability nightmare. We found ourselves facing two choices. We either promote an asynchronous replica, and we risk potential data loss, or we suffer additional downtime by manually initiating a failover to our standby cluster in our standby region. So for us, of course, data loss is an unacceptable option, and so we chose the latter approach. So what the heck just happened here? Well, after further investigation, we found that a network switch had partially failed and was operating in degraded state. The rack with the misbehaving switch included one server in our etcd cluster which handled the leadership election. So when a cluster leader fails, etcd utilizes the RAF protocol to maintain consistency and select a new leader for promotion. However, there's a simplification of the RAF protocol, which all members just need to state whether they're available or unavailable, expecting them to provide accurate information or not at all. So this works well for full failures like machine crashes, but you run into cases of undefined behavior when different nodes in your RAF cluster start telling each other different things. So in this case, we have node 1 and node 2 and node 3, which had degraded network switch, so the network link is degraded between them. And so node 1 didn't think that node 3 was any more a leader, but node 1 and node 2 still had a link, and node 2 and node 3 still had a link, and node 2 acknowledged that node 3 was still the leader. So in this situation, node 1 tried to initiate many leadership elections, and so it would continuously vote for itself, while node 2 still saw node 3 existed and would vote for node 3. So what happened here? Well, we get into a deadlock state where no leader is elected, and when we get into a deadlock state, then the cluster becomes read-only. Now, because the cluster is read-only, clusters in both regions are no longer able to communicate with each other. And this initiated both clusters to actually fail over to the primary replicas that we saw. Now, typically when we fail over, the synchronous replica is promoted, but what happens to the old primary? Well, when we fail over, the synchronous replica is promoted. The old primary needs to actually begin undoing transactions that it has committed, because there could be some transaction history that could have diverged between the new primary and the old one while we kept it available under a network partition. After it unwinds all the way back, the diverged history is unwinding our diverged history, kind of like a Git branch being undone. The synchronous replica needs to then send over and basically receive and replay all the new and correct transactions that are happening on the new and correct primary that it missed. Our primary failed once again because we had no more synchronous replicas to absorb the RPS. And so once the primary failed, there was no longer a synchronous replica, meaning that we had downtime. But also, we need to figure out why was it taking so long for the synchronous replica to try to replay all of those transaction logs from the new primary. So there's three things going on here. I mean, this is a pretty large scale issue, right? Number one, we have a hardware failure. That kind of is just an unfortunate situation that happens. Number two, we had a Byzantine fault with Raft. Now, this is a really rare event, and it's known with the Raft consensus protocol that this is a faulty situation. But most implementations of the Raft cluster or the Raft consensus protocol will choose to use a simpler algorithm versus something that uses cryptographic hashing, but is harder to understand. And our third problem here was that Postgres was taking a very long time to resynchronize when the primary was sending back the write-ahead logs for the new synchronous replica to replay. So for us, we decided to pick the third option to solve because this was under the most control, actually optimizing Postgres internally. So typically when you have the write-ahead log, this is kind of what it looks like. You have the original timeline with the original history. You have the old timeline, which kind of diverges on its own path because it's no longer communicating with the original one and receiving replica write-ahead logs. So what we actually found when digging into our logs was that most of the time, Postgres was spent in rsync, just copying over 1.5 terabytes of log files from the primary to the old synchronous replica that was resynchronizing. So what's the solution here? Well, we optimized Postgres by, instead of reading all the way back in the history of time and copying those files, we just went back to the last diverged point where the timeline forks. And then we just need to copy off files from there. That's like 5% of all the data that was originally copied. So doing this, our replica rebuild times reduced from 2+ hours to just 5 minutes. So that's like a 95% speed up. We also submitted our patch for open source contribution. And as another cool feature, now we're able to resync and do this whole failover resync in our cross-cluster failover and resynchronization across multiple regions. So what are the key lessons of this very confusing but large-scale incident? Well, number one, we need to anticipate the effects of degraded state and not just fully failed state. And so for this, we actually have some internal tools that do chaos experimentation randomly on a cluster, which is kind of a little bit out of scope for this talk. But also another thing we found is that it's quite a good investment to go and build and fix software and open source yourself. You build the in-house expertise that otherwise would be very hard to find. And it's better than just trying to go figure out, oh, we should just use this as a separate tool because we're having problems with this one. You don't know if it's going to be any better. And so that's our open source commit that we're sending off for Postgres Commit Fest. And I'm going to hand it back to you, Vignesh.
Yep. Not fun, right? Just maintaining one cluster in one region, you can think about all the different failures, like hardware failures. Even some of the failures, if they fail cleanly, that's so much better. There are cases like these Byzantine hardware failure, where components are not fully failed, but they are actually operating in degraded state, which is much more challenging to figure out than actually building your systems and architecting for full failures. So now we take this monolithic like Postgres clusters in couple of regions and distribute them across 4 regions or 3 regions. And they will pretty much look like from an edge application. Let's take a Cloudflare workers standpoint view. It will look like a cluster of clusters. So this is where we are currently heading down to. So we had like primary region based out of pretty much most of the time in the US. We spread it to EU. Within EU, we have like a couple of regions, and then now we are branching to Asia. And pretty much all of them uses Postgres streaming replication, especially using the hub and spoke model, where we have the primary region which replicates to all the regions. There is no like a cascading replication involved here. We have to watch out for all the fun things that Justin mentioned about like replication lag. Keeping all of them in sync is important. And also when there is a very high replication lag, we have to somehow make sure that we address the SLAs that we have provided to the application teams. Sometimes, which means we have to divert the traffic to all the way back to the primary region itself. And having this kind of distributed Postgres is cool, but what is the actual benefit? Like where can we kind of use the strengths of a distributed Postgres? So this is when we introduced smart failovers. Look at this new topology and figure out which region could be the primary. One of the first attributes is like pretty much as simple as like follow the sun. Hey, keep your primary region, keep moving as it progresses. For example, like start with US, and then when the day ends, move your primary region back to the Asia, which pretty much solves the latency problem, because your writes are going to be much faster since your primary database is closer to the vast majority of population or clients' applications. I mean, all we are trying to do is still we are working around the fundamental limitation that Postgres is pretty much a single primary system. If Postgres can be made like a multiple primary without a lot of the downsides, we don't actually need to do a lot of these dance. The second one is sometimes we have done based on the capacity. Certain regions have more capacity than other regions. For example, like shipping hardware to a particular continent has become challenging, especially during COVID. For example, we couldn't get hardware to Asia in time. So we had to pretty much keep most of the time our primaries away from Asia. The traffic, which I already touched upon. And the last one is the compliance-based, where we are getting into more and more challenges that, for regulatory reasons, we have to have certain kind of data in certain region. And how do we do them? And that's, once again, we can do that using smart ways. So if you think, okay, well, it's not that simple. Seems like you have Postgres in one region and then put them out in 5 regions and whatnot. Well, then keep failing over. And some of the optimization, especially what we talked about earlier about PG rewind, using that we can rebuild the clusters pretty much in less than 1 minute. So you have your primary region in US, fail over to Asia. What happens to your primary region used to be a primary region in US? You can rebuild that within a minute, which is good. So that seems like we can keep doing this all day. Well, to be honest, it's not that simple. One of the biggest challenges that we ran into is the dependency graph. Right? If you think about it, well, just failing over your databases is not that hard, at least fairly hard, but still at least seems like a solvable problem. But the biggest challenge comes in when you bring in your applications inside this. How do we do just your databases without failing over your entire applications? Especially nowadays, applications are duct-taped, like with multiple components like message queues and Kafka and analytical databases. It's just not easy. So anyone who is here thinking about like, hey, I'm just going to do this cross region and I'm going to like, failover, just look at your application dependency graph. Even not just like first layer of application dependency, you have to like go all the way down, like track down all the dependency layer, because even the last one of the dependencies is still going to like, suffer from a network call. Yeah, the other big aspect is it requires a lot of coordination. At least we haven't still completely automated, so we have to like jump on a bridge call across 20 different team members from different teams, figuring out how to do this. Yeah, in our case, it's something like this, a dependency graph. For example, like you have databases that pretty much the first layer of, or like level 0 of dependency. Then you have like fundamental systems, like for example, entitlements, like billing and authentication and configuration, which pretty much being used by rest of, let's say, like a primitive applications like R2 and SSL and whatnot. Finally, I just want to quickly touch upon the database trends, especially as a practitioner that I have been looking at and have some kind of knowledge. One, we are looking at more of providing embedded data at the edge, where we are still keeping your monolithic Postgres at least like 3 to 4 regions, and then bring a lot of those key data to embedded database, for example, SQLite. So we can keep your Postgres still as a somewhat monolithic or as edgy, and then keep real edge using your SQLite. And especially when you are using SQLite at the edge, make sure that it is still like Postgres wire compatible. So there are open source projects where they take the Postgres wire protocol and then replace or underneath put SQLite as the storage engine. So in that way, that applications feels like they are still talking to Postgres. The other idea is that persistence at the edge, where obviously Cloudflare workers and whatnot, others are definitely looking at bringing more like client-side data. The other interesting one, which you folks might have noticed, is bringing more of separated storage and compute. For example, the typical architecture where we have like Cloudflare workers running in Europe, whereas your database is in North America. However, that's changing. A lot of the newest features are where we are bringing or co-locating both your storage and the compute. Even for example, Cloudflare Workers has a new feature called Smart Placement, and pretty much what it does is it moves the Cloudflare Workers close to where the database is. Earlier, we pushed the code more close to the clients. But what we noticed is that a lot of those client applications are actually spending a lot of time talking to their database. And pretty much any business application is like chatty, right? They want to like talk to the database 5 times to even respond to a single request back to the clients. So we pretty much, like a full circle. We moved out the compute close to the end users, and now we are slowly bringing back those compute back to where your database is. And lastly, this is another one where we are running into a lot of new challenges, is how do we do this data localization, especially for Europe region, and still using Postgres. And this is where we are betting heavily on logical replication. So logical replication provides the flexibilities where we can even replicate on a row level, on a specific column level. So still, this is a little bit I would say in a more of an exploratory phase. We haven't yet made anything production using logical replication, but I have a strong feeling that it's going to be this way. So the areas we didn't cover a little bit, happy to sync offline, is one of the multi-tenant resource isolation. That's altogether a separate kind of problem. Like how do we keep every one of them as a good citizens, right? Like noisy neighbor problems, etc. So we haven't touched upon that. With this, I am wrapping up. Thank you very much, and happy to take any questions.